Good morning. Great pleasure to be here this morning. And thank you for our Canadian colleagues for taking the time to travel and come to Maine. I've been working at the University of Maine for over 30 years. I came in here as a young, foolish person and joined the faculty here at the University of Maine. It's a wonderful institution. A bit about the university. Most people don't know we have 500 PhDs within an area of about a square mile, and so we have more PhDs per square mile than any other place in the state of Maine. So this is a good thing, and it's a bad thing at the same time. So, as most of you know, being one of them. The center I work in is called the Advanced Structures and Composites Center at the University of Maine. It's hopefully this afternoon, many of you will get a chance to see it. We started constructing the lab about 20 years ago, and usually every about 3 or 4 years we add more to it. So we have about 100,000 square foot lab, about 180 people who work there. So if you have an opportunity to come see it this afternoon, we'd love to show it to you. I'll be there to do that. I'll tell you a bit about Canada. My son is an ice hockey fanatic. And about a week ago, he brought me to his room at about 11 o'clock at night. He says, "You know what my plan is?" I said, "What's your plan?" He said, "You see this big empty wall here in my room?" I said, "Yes, I want to get the biggest Canadian flag and put it up on the wall and cover it up because he likes the Canadian hockey team." So with this in mind, we hope we can develop some other opportunities to collaborate. The University of Maine had a great hockey team. If you have an opportunity to go see the Alfond Arena up here, we are fanatics about hockey here in Maine, very fanatics. We have a lot of Canadians who play on our hockey team as well. So I'm going to talk about offshore wind a bit today, and my goal here is to look 20 years down the road. And not today, and what we can do next week or next year or next month, but let's look at 20 years down the road and what could happen. One thing we'd like to do in Maine is use our offshore wind energy to help heat our homes, to help fill up our cars of the future, electric cars of the future, and help jumpstart the economy. This picture here is a picture of the first offshore wind, grid-connected offshore wind turbine in the United States. It was built on this campus, designed by a team on this campus. We had 30 companies from across Maine and the US who worked with us, and we deployed that in 2013. And the hull is made out of concrete, and it floats, and the tower is made out of composite materials. And our goal here is to build some bigger ones, and a lot of them in the future, so we'll talk about that. So why are we working on offshore wind in Maine, and why are we interested in it? This is our lab, by the way. If you get a chance to see it, come and see it this afternoon. So it's 100,000 square feet. The upper part of the lab on that corner right here is the new ocean engineering edition that Chris and I and many others have worked very hard on over the last few years. A bit about Maine. We started getting interested in offshore wind in 2007 and 2008 when we were paying $4 a gallon at the pump. And many of us use heating oil to heat our homes. When you pay $4 a gallon for heating oil and gasoline, it just so turns out that the average family in Maine at that time was paying $10,000 a year just for energy costs. And electricity was not the problem. If you look at the numbers down here, the average family paid $1,000 in electricity costs, $4,000 to heat their home, and $5,000 to fill the two cars in gasoline every year. So the average family in Maine has 2 cars. So the problem here is not electricity and energy. People think electricity and energy are equivalent. Really, it isn't. The problem we have in Maine, for our family at least, our families, are the cost of gasoline and heating oil. So if we're going to make a difference in the long run in the state of Maine, we've got to figure out how to bring those costs down. And this is at $10,000 when at $4 a gallon. The average family income in the state of Maine is $45,000. So 10 out of 45 is a big chunk of the 45,000. Over 20% of our family income is oil. Today we're near $2 a gallon, so we have a little bit of a reprieve, and we all know that reprieve is not going to last. We have a little bit of a reprieve. At $2 a gallon, we still pay a lot. We still pay $5,500. He wants to restart. No, not now. Okay. It's amazing what Microsoft does for you here. Okay. So $5,500 a gallon. $5,500 is what it costs the average family in the state of Maine today in energy costs, and that's very high. Let's put that together, all for the state of Maine. What does the picture look like? According to the U.S. Energy Information Administration, in the state Maine profile, in 2013, $6 billion left to the state of Maine in fossil fuel costs. These are monies that we had to pay off for countries outside Maine and for other places in the United States in fossil fuel prices. And to put that in perspective, the average, the entire state budget in the state of Maine is $3 billion. That's everything it takes, all the taxes that we pay, all what we pay for education, for healthcare, for schools, for roads, for bridges, is $3 billion, and we pay $6 billion in energy costs leave the state of Maine. So that's twice the family, the entire income and taxes in the state of Maine. So what does that mean? That's $6 billion that we have no control of. We sit down in Augusta, Maine. This is where we make our policy decisions in Augusta, and we worry whether we can reduce our taxes by 1 or 2 or 3%. Whereas we're paying twice our taxes, $6 billion in energy costs, we have no control, not one control on those costs. Okay? That's the challenge that we have. So how much electricity does the state of Maine use? Not a lot. Okay? We're a summer peaking state, meaning that the most electricity we use is in the summertime. We use about 2.4 gigawatts of electricity in the summer. That's the capacity we use. When we have a lot of tourists that come to Maine and come to Maine and go to our hotels and turn the ACs on, that's when we have the highest use of electricity in our state. We have also a winter peak, but it's smaller than the summer peak, 2.4 gigawatts. To put that in perspective, if you don't work in the energy world, a gigawatt is roughly a good-sized nuclear power plant. Okay? And if you build 2 nuclear power plants, you can power the whole state of Maine. Okay? Not that I'm recommending that, but that's what you take to do. So how much offshore wind do we have off the coast of Maine? Within 50 miles of the coast of Maine, there's 156 gigawatts of offshore wind. It takes 2.4 gigawatts to power the whole state of Maine. So we're very energy rich. We just don't do anything about it. That energy is just sitting out there, and we're not doing anything about it. So in 2007 and 2008, we decided to do some work, to do something about it. So we started a major research program to figure out how to bring this energy cost effectively back home. Okay? And not only to turn the lights on, but to heat homes and to fill up cars of the future. Now, if you look at the east coast of the United States and you work your way from north from Florida to Maine, the best offshore wind resource is in the Gulf of Maine. So the higher, the more north you get, the better the wind resource gets. That's the red and the oranges you see out there. And of course, the entire northeast and New England area has a lot of wind. And if you keep traveling, of course, north towards Canada, that's also true as well. You have a great offshore wind resource. So where does offshore wind sit around the world? Europe is the world leader in offshore wind. They built the first offshore wind farm in 1991, when many of our students here weren't even born. So they've been building offshore winds for a long time, and that's accelerated quite a bit since then. This year, there are near 12,000 megawatts of offshore wind installed in Europe today. The leaders are Germany, the leaders are the UK, and they're moving fast and furious in installing these offshore wind farms. And one reason is that they don't think they can rely on natural gas from the Russians. They don't trust the Russians, and therefore they want to try to develop some of their own resources to reduce the risk from shutting off the pipelines from Russia. So how do they build offshore wind farms in Europe? They use fixed bottom turbines. What does that mean? The turbines are fixed to the seabed. They have very shallow waters off the coast of Europe, most places, typically 40, 50, 60, 70 feet of water. And so what they do is they typically build a foundation to the seabed. And the most common foundation, fixed bottom foundation, is called a monopile. What's a monopile? It's a big steel column, 20 foot in diameter, about 2.5 inch thick walls, and you pound into the seabed. Just like you take a nail, you pound a nail into a piece of wood. Think about that nail being 20 feet in diameter, okay? And you're pounding it into the seabed 50, 60, 70, 80 feet, okay? And needless to say, it takes a heck of equipment to do that. To pound a big steel pile 20 feet in diameter into the mud, into the seabed, it takes jack-up barges. You could see them right out there. And it takes cranes to lift the turbines up. Where Europe is today, the turbines are getting bigger and bigger and bigger with time. And why? Because it drives the cost down. So there's a big race to build bigger turbines by the turbine manufacturers. The biggest turbine available today that's actually operating today is 8 megawatt. Single turbine, that's 8 megawatt. That's how big they are. The 6 megawatt turbines are becoming more and more common right now. They're closing on financing on farms with 6 megawatt turbines as we speak, 400 or 500 megawatt farms. So 6 megawatt turbines, to give you an idea of what that is, the rotor diameter on a 6 megawatt turbine is 500 feet. 1 2/3 football diameter, football field diameter. Think about that, 500-foot rotor. The hub heights are 300 feet. So the distance from the water level to the hub is the height of a 30-story building. And the rotor diameter is 500 feet, so it's about a 50-story building. Think about how big these things are. These are big, big machines. Now, if you go to our lab this afternoon, you'll see some of those blades we're testing in our lab. It's not 500 foot, it's 180-foot long blade, but you'll see it in our lab this afternoon. But so this is how they're doing it in Europe. Do you think that's cheap? Now, just to give you a sense, a jack-up barge alone will cost you $200,000 to $300,000 a day to run. And then you're paying for it whether you could use it or not. If the weather goes bad and the jack-up barge has to shut down, you're still paying for it. Okay? So it's a very expensive proposition, and offshore wind in Europe has been expensive. So can we drive the cost out? So one of the solutions we have, and in Maine we have deep waters. In other words, if you're 3 miles off the coast of Maine, you have 300 feet of water. And in 300 feet of water, you're not going to build a foundation to the seabed. You couldn't afford it. Okay? And therefore, we've started working on floating technologies, wind turbines that can float on a floating foundation. And that's a picture of the floating foundation we built in 2013 and put out in the water. This is a 1:8 scale of a 6 megawatt machine. So basically, if you've seen the movie Honey, I've Shrunk the Kids, okay, we've taken the turbine and shrunk it by a factor of 8 in this case in terms of size. And it's a lot more complex than that, but that's basically what we've done. The hull you're looking at is made out of concrete. So it's a concrete hull. Why? Because we have concrete here in Maine. Why? Because concrete doesn't corrode in the water. And why? Because concrete's cheaper than steel. Okay, that's the reason we went in that direction. And then this is a concrete hull, and it has 3 flotation columns. You can see them at the corners. And I take this almost everywhere I go. My wife says you sleep with this thing, but I don't. Okay. But this is what these floating turbines actually look like that we've developed. We call it the Volturnus floating wind turbine technology. To give you a sense of size, again, the rotor that you're looking at is 500 feet, the height of a 50-story building. That's the rotor alone. The flotation columns you have on the 3 corners are 30 feet in diameter, each one, and 120 feet tall. So each one of these flotation columns you see on is basically a big can of concrete full of air. Okay, that's what that is. And it's 120 feet tall, meaning it's a 12-story high building. So if you go to Bangor, Maine right now, you won't find a 12-story high building. So this is 3 12-story high buildings, okay, that hold up the unit that makes it float essentially. It's a trimaran. How many of you have sailed a catamaran? Okay, this is a trimaran. So it's got essentially 3 hulls that make it float. How do you make a catamaran more stable? What would you do to it? You'd make each hull bigger, right? And you put the hulls farther apart, right? Then the cat's more stable. And this is exactly what we're doing here. We have 3 flotation columns, and they're 150 feet from the center. Think about if you had a catamaran that has a close to a 250-foot beam. That'd be a heck of a stable catamaran, right? And that's what we've got here. We've got a almost 250-foot footprint diameter on this hull. So the hull fits in a circle of 250 feet. So that's what this looks like for a 6 megawatt machine. So we built a 1:8 scale version of that, all made out of concrete. We built it in our lab, which you'll see this afternoon. Lots of excitement in Maine. As you see, a lot of people there. We had close to 3,000 people attend the ceremony. We prefabricated the whole thing, lifted it in one piece, placed it in the Penobscot River about 10 miles south of here, and we towed it down the Penobscot River using a tugboat. And you can see it right here being towed down the Penobscot. Oops. No, what happened now? Here we go. So this is the hull being towed down the Penobscot River and out into the ocean. We use the Maine Maritime Academy tugboat. Notice that the whole thing's assembled. Yeah, it's 3 flotation columns. You see them on each corner, and the hull and the tower and turbines on top. And then we don't need jack-up barges anymore. We don't need heavy cranes out in the ocean to assemble these things, right? So we cut costs down quite a bit that way. Yeah. Oops. Again. Microsoft attack. Okay, postpone. All right, so So notice how stable it is on tow out as well. During the tow out operation, one of the key things is for this technology to work is you want to be able to tow it out at reasonable speeds from shore. But think about the unit about 8 times that size being towed down to sea. That's what we plan to do next. And our next program is to build a full-size version, 2 full-size versions of this unit, and place them off the coast of Maine about 14 miles offshore. We've been working at this for a long time, and we're competing right now for a Department of Energy grant, a $40 million grant to allow us to move forward with this program. And by the way, we are already collaborating with Canada on this. This is what it looked like off Castine. So when we got to Castine, we had 3 mooring anchors, mooring lines, just like you have on a ship, 3 steel chain mooring lines that are to the seabed, and they connect to each one of the flotation columns. As you see here in this, you see the 3 chains we have at the corners. These 3 chains basically keep it on station. They allow it to move around a little bit, but they keep it on station. We had a pre-existing undersea cable that we connected to the turbine when it arrived to the site, and we ran it for 1.5 years. It had over 60 sensors on the hull that told us how it moved, how it responded to the winds and the waves. And the good news is we were able to prove that our models work. And this is a short video that shows you one of the storms that we saw on December 15th, 2013. This is a winter storm called Winter Storm Electra that hit. This is 2 o'clock in the afternoon on December 13th, 2013. And in this case, we had close to 45-mile-per-hour winds, and the wave height relative to the size of the hull were a 50-year return period wave environment. So this hull right now, as you see it, is in a 50-year return period storm. Okay? And in this case, you can see the hull is barely moving. You can't even see any movement on it in a 50-year storm. We saw actually a 500-year storm relative to the size of the hull. In a 500-year storm, it only moved off axis by 7 degrees. That's how much it tilted off axis. So it's a very stable hull. We proved our models, and now we have all the data we need to go build the big one, in essence. So that's why we're getting the financing to do so. And the team working with us to build the big one includes a Canadian company, which you know all. Emera is a partner on this project. Chimbro is a partner in Maine. So the success of that program now is getting the Department of Energy to be very interested to build the full-size units. The full-size units will go off the Monhegan Island in Maine. It's an island that's about 14 miles offshore. The University of Maine has 2, we're going to place 2 of these units off Monhegan. You can see what the units look like, 2.5 miles south of Monhegan Island. We're going to have sensors, of course, like we did on this other project, and we're going to monitor this for 5 years once we build it. We also have a LiDAR right now placed on Monhegan Island. It's a floating LiDAR that allows us to measure wind speeds at hub height. It was also built in our lab. This has about 2,000 pounds worth of batteries on the LiDAR. Essentially, it's a laser that measures wind speeds at hub height. If you build a wind farm on land, you put an anemometer tower, right, to do that. You can't put an anemometer tower cost effectively when you have 300 feet of water. Okay, that would be a $20 million anemometer tower that nobody could afford. But that's why we built this thing here. We built this thing with Neil Pettigrew is the key of the person. Neil, you might raising your hand. It's really, this is Neil's baby right there, and he's been building these mid-ocean buoys here for what, 15 or 20 years now. It builds them and sends them all over the world. And without him, we wouldn't be doing this. So that's him and his team. But we have essentially a laser in there that measures airborne particulates and allows us to know what the wind speeds is at hub height at 300 feet. So what happens if we actually do this? If this whole program actually comes into play, the goal is to build 5 gigawatts of offshore wind off the coast of Maine by 2040. Now, remember I told you we're looking 20 years down the road here. That's the plan. If we did that, if you built 5 gigawatts, you can heat every home in the state of Maine with that energy, and you can fill every car of the future if we use electric cars. So I'm almost done right here. How many of you think you might be buying an electric car in your lifetime? Thank you. I asked that question to, I give talks to high school students, quite a few talks. I usually have about 500, 1,000 students in the classroom. When I ask them that question, guess how many hands go up? Every one of them. Every one of them. Every major car manufacturer has an electric car today. Now, why this is important? Remember I told you in Maine, the cost of energy is not electricity. The cost of energy is heating oil and gasoline. So therefore, if we had electric vehicles, we can fill up our cars using offshore wind and drive costs out over the long run. Plus, electric vehicles can become a storage medium for offshore wind. So basically, most of us use our cars 1 to 2 hours per day, and the rest could be connected to the grid and actually could be a free storage device, distributed storage device for wind, for offshore wind. So that's that's the vision that we have. Heating using air-to-air heat pump or ground source heat pump is the most efficient way to heat our homes. If you couple that with offshore wind, that's another way to drive costs out. So in the long run, then our goal here is to use offshore wind in the state of Maine to fill up our cars, heat our homes, and jumpstart our economy. And that $6 billion we talked about that leaves the state of Maine every year, maybe we can keep a big part of that here in our state. And we'll look forward to collaborate with you because, by the way, you have the same offshore wind resource that we do. You have deep waters like we do, and there's great opportunities to collaborate. Thank you.